The isolated footing is the simplest and most popular type of foundation. However, if a crucial check is left out from the design, or if a critical load combination is ignored, then structure life could be adversely affected. Moreover, footings that are over-designed tend to increase construction cost and time, as they usually call for deeper excavations that may require shoring and strutting, dewatering, rock drilling, or rock blasting. In general, design of an isolated footing entails focus on
multiple load combinations, multiple support joints, 6 load directions, reactions applied at pedestal level, maximum soil pressure, limited loss of contact, 2-way shear, 1-way shear, sagging flexure, hogging flexure, uplift check, sliding check, overturning check, optimum economy.
Design for optimum economy is both laborious and baffling, even for sophisticated software. Optimizing footing costs based on unit rates of concrete and steel is therefore arduous, and with multiple load combinations even more so.
After extensive efforts on design automation, our R&D team has finally come up with a user-friendly application that designs footings to international codes and handles up to 500 load combinations, thanks to our MD, Syed Haider, for his innovative approach, critical thinking, and motivation. As a result, we do not have to club maximum support reactions from various load combinations into a single one to obtain the governing load case.
6 output sheets containing methodically elaborated, accurate calculations are produced at the click of a mouse. Above all, the footing so designed is the most economical one, insofar as the material costs are concerned. And the automation enables us to absorb the changing needs of our clients without affecting design cost, schedule, or quality.
The algorithm is simple. With the minimum dimensions and limiting aspect ratios provided as input, numerous footing sizes are arrived at by exhaustive permutations of the 3 footing dimensions. Then, starting with at least footing size, design checks are performed based on design code, complying with good engineering practices. For a footing to be considered successful, it must satisfy the required design criteria for all load combinations at all support joints. Cost is then calculated for successful footings using the material rates for concrete, rebar, and formwork to arrive at the one with the least cost. Comprehensive calculations are then printed for the least cost footing, thus completing the footing design.
We start by opening this application. That takes us to our first input page for support reactions. Here in a separate worksheet, we have support reactions for braced bay columns of a pipe rack, for which we intend to design the footing. Bases are pinned, so moments are all 0. We copy this from here and paste it in our input sheet. And then we go to the next page.
Load combinations are automatically copied here from previous page. We use this facility to fill in SBC increase factor, along with other safety factors, by their default values. These predefined values are generally based on the design basis for ongoing project, in order to save time. These can be changed, based on project design basis, if required to be different for specific load combinations. For example, let's say this one is a wind load combination that allows for 33% stress increase. Here we can reduce the restoring moment for overturning check, if required. Say we have it as 80% for wind load combination.
This input page allows for selection of some key design options as shown. Our structure being a pipe rack, reactive forces are at pedestal level. We will select all 6 forces, as all of these would be transferred down to a footing level in absence of tie beams. We want our footing to be checked in uplift, sliding, and overturning. We can as well disable stress increase here, if required, without having to go to previous input sheet. We will keep this selection on, so the base pressure would be increased appropriately for selected load combinations. Loss of contact between footing and soil can be limited here. We set the maximum to 40%. We want the footing to be checked in uplift with 80% backfill. The same can be 100% for sliding and overturning checks. It is important to note that these values apply to all load combinations. Let us select the design code as IS456. This takes us to our next input page.
We start with default input. Our footing for the pipe rack column is an edge footing. Selection of the correct column location is important, especially for buildings with elevated floors such as warehouses, where soil overburden varies greatly with location. In the case of pipe rack, this hardly matters. It is worth mentioning here that the axes shown for footing are structure global axes. We do not have any plinth beam, so we leave this blank, and non-relevant input gets erased. Pedestal projection is 300. Plinth height is 0. Water table depth is, say, 1 meter below ground. Footing depth is 2,000, and minimum footing thickness is 300. This takes us to our final input page.
Material properties can be entered here against respective description in the units indicated. Apart from material grades, limiting bar dimensions, and soil parameters, this input page contains fields for unit rates of concrete, steel, and formwork. These values need to be entered with caution, as they will determine the size and steel ratio for the most economical footing. Again, we use this facility to fill in the input fields automatically. Friction coefficient between soil and concrete is required as we have opted for sliding check. This drop-down menu currently has just one item representing economical design. And this initiates the footing design. Because of the load combinations, the processing time is over a minute. And so we fast forward this.
Let us quickly go through the calculations. The governing load combinations with respective node numbers for maximum soil pressure, uplift, sliding, and overturning are all highlighted here. This is followed by input echo for dimensions, materials, soil data, and levels. Computations start with assumption of footing dimensions, which, as we will see later, correspond to the most economical footing. These are along structure global axes.
First design check is for base pressure. If governing load combination involves SBC increase, then support reactions are adjusted accordingly. This is followed by calculations for buoyancy, soil volume, soil weight, and other loads. Some of these being 0 for pipe rack footing, until we finally arrive at the total vertical load and biaxial moments under the footing. Figures show the possible scenarios for base pressures in the two directions. This is followed by eccentricity calculations. If one or both eccentricities exceed corresponding Kern distance, the maximum base pressure gets modified according to Teng's chart for permissible LOC, thus giving us design maximum net pressure to be compared with soil SBC. This is followed by calculation for maximum factored net pressure that will be used in subsequent calculations.
Next, we have the check for two-way or punching shear. Effective depth is calculated for bending about each axis. PXO and PZO are as indicated here. Cases where one or more of these exceed corresponding footing dimension are also accounted for in design. The intricate calculations are simplified for easy checking and contain formulae that are written using both variables and numbers. And at the end, we have the action versus strength comparison. We then have the design for flexure, starting with bending about global z-axis, for sagging moment first, and then for hogging moment. In any case, minimum top steel is provided where footing thickness exceeds a specified value.
Similarly, we have these calculations for bending about global x-axis. The moment at critical section is checked against the moment of resistance with assumed bar diameter and spacing. This is followed by check for one-way or bending shear, first for shear in GX direction and then for GZ direction. References to relevant clauses of the design code are indicated as applicable.
Because we opted for uplift, sliding, and overturning checks, we have these calculations that start with overturning check. Overturning moment is calculated about each axis and checked against restoring moment to have the required factor of safety. This is followed by check for uplift. And, finally, the sliding check. The sliding criterion may govern the design where structure is subjected to significant lateral loads, such as from an earthquake or blast, or from pipe anchor forces, as in here.
The last output sheet contains footing layout and rebar details on plan and in section, as shown here.
Now a little of the programming background. We open a worksheet that contains a multitude of footing sizes as explained earlier. The ones in blue are those that were able to withstand all load combinations at all support joints. The others obviously failed in some limit state for at least one load combination. Let's examine the one here. So this one failed under this load combination at this support joint and is therefore discarded. In other words, footing sizes highlighted in blue are all safe.
Here's another worksheet summarizing footing dimensions, rebar details, and various costs for each successful footing, 49 of them. Each row represents an individual design. The common factor is that they all had at least one limit state for which the design was critical, yet safe. That is to say, none is an over-design. It's just that where a larger length was beneficial, it might have gone for a larger width or thickness, and so on. The software has highlighted this one as the most economical size. This can be confirmed by arranging the table in ascending order of footing cost. The size and rebars for this are exactly the same we saw in the calculation sheets. As structural engineers, we all know that manual design of an isolated footing requires a guess size to begin with. And if your guess happens to be something like this, you can imagine where your project costs can go.
Now let's try designing a spread footing for braced bay columns of a PEB, say a warehouse, for the same support reactions. We start with design options. Let's say the warehouse length is along global Z. So here, we deselect FZ and MX, as those forces won't be transferred down to footing level in view of a tie beam along building length. We leave the rest of the values unchanged. This dimension here is equal to the gable frame spacing, say 8 meters. So now we have additional loads from block wall and tie beam. Most warehouses have 4 feet high plinth. And this completes the footing design. Here we have the footing details. Dimension along the direction of tie beam has reduced considerably, for obvious reasons.
The footing design for pipe rack is as per the highlighted row, and it corresponds to the most economical design. Can we have design calculations for a different footing, say for option 14? Yes, we can. In here, we have this drop-down menu that includes the list of all successful footings. From the list, we select option 14. And this completes the design. We have got calculations for footing of our choice. This feature can come in handy when dealing with projects for structure retrofit and for pipe rack adequacy checks, where existing footings need to be checked for additional piping loads. By a judicious choice of limiting dimensions and aspect ratios, the software is made to design a footing with identical dimensions as existing one for revised loads on the structure. If steel required by design does not exceed that available, then the footing is considered safe for new loads.
Epicenter.
With us, your structure is in safe hands.